The art of the curve. Navigating the world through parabolic coordinates. Imagine stepping away from the rigid straight lines of a standard graph and entering a world defined by sweeping, elegant curves. In this system, known as parabolic coordinates, we locate points not by moving left, right, up, or down, but by finding the intersection of two families of mirrors. One family consists of parabolas opening downwards, while the other consists of parabolas opening upwards. The magic of the right angle. The secret sauce of this system is its orthogonality. Even though the grid is made of curves, every time an upward opening parabola crosses a downward opening one, they meet at a perfect 90-degree angle. This geometric harmony is crucial because it allows scientists to break down complex three-dimensional movements into simpler, independent parts, a process called the separation of variables. Quantum landscapes. The Stark effect. One of the most famous uses of these coordinates is in the world of subatomic particles. When a hydrogen atom is placed in a uniform electric field, the standard spherical symmetry of the atom is broken. The electric field tilts the energy landscape, pulling the electron in a specific direction. In a standard grid, the math for this would be a nightmare. However, because parabolic coordinate lines naturally align with this tunneling path and the tilt of the field, the complex quantum equations become solvable. This allowed pioneering physicists to accurately calculate how spectral lines, the fingerprints of light from atoms, split and shift under electrical pressure. The knife edge mystery. Potential theory. Parabolic coordinates are also the natural choice for studying edge effects. Consider the razor-sharp edge of a conducting metal plate. If you were to look at the electric field near that edge, you would find it becomes incredibly dense and intense, mathematically infinite at a perfectly sharp corner. By using a parabolic grid, the metal plate itself can be treated as a single coordinate line. The rest of the grid then wraps around the edge like a protective cloak, following the flow of electricity or even the flow of a fluid moving around a sharp obstacle. This transformation turns a chaotic physical boundary into a simple, manageable problem. Visualizing the system through demos. To truly understand this system, one can look at several visual demonstrations. Grid construction. An animation showing how sweeping through different values creates a 2D plane covered in red and blue confocal parabolas. The tilted potential. A visual showing a spherical atom deforming under an electric field, with a parabolic grid overlaying it to show the new symmetry. The sharp edge. A simulation of field lines crowding around a knife edge, demonstrating how the coordinate lines act as perfect boundaries for the energy flowing around the point.